for the header. ATM architecture. ATM operates as a connection-oriented network. Before data is sent, a virtual circuit, path, must be established between the sender and receiver. 1. The reference model. The architecture is divided into 3 layers. Physical layer, manages the transmission of bits over the medium, like fiber optics. ATM layer, handles cell routing, multiplexing, and congestion control. ATM adaptation layer, AAL converts higher-level data, like an IP packet, into 48-byte segments for the ATM cells. 2. Virtual connections. Virtual channel, VC. The basic unit of connection. Virtual path, VP. A bundle of virtual channels that are routed together, simplifying network management. Use in telecom networks. In the peak of its usage, ATM served as the backbone for telecommunications infrastructure. Broadband ISDN, BISDN. ATM was the chosen technology for the next generation of digital integrated services. DSL backhaul. For many years, when you used a DSL modem at home, your data was encapsulated into ATM cells to travel from your house to the provider's central office. Core switching. Telecom giants used ATM switches to mix telephone calls, voice, and internet traffic over the same high-speed fiber lines. ATM was designed to be the everything network. In the 1990s, telecom operators faced a major problem. They had separate networks for phones, circuit switched, and the internet, packet switched. ATM was the solution intended to unify them into a single infrastructure. ATM as a backbone network. In a telecom backbone, ATM acted as the high-speed glue that connected different regional networks. Core switching, massive ATM switches sat at the center of the network, routing millions of cells per second. Because ATM is connection-oriented, the backbone could guarantee specific paths and speeds for different types of traffic. Carrier of carriers, ATM often ran on top of SONET/SDH, synchronous optical network, fiber. While SONET provided the physical speed, ATM provided the intelligence to slice that bandwidth into virtual paths, VPS, for different customers or services. Integration of different services. ATM uses the ATM adaptation layer, AAL, to handle different types of traffic. This is how it integrates services. Voice, AAL1 converts continuous bitrate voice calls into cells. It ensures low delay and maintains timing so the voice doesn't sound robotic. Video, AAL2 handles compressed video which varies in speed but still needs to arrive in a steady stream. Data/internet, AAL5. This is the most common layer. It takes large IP packets, chops them into 48-byte segments for the ATM cells, and reassembles them at the other end. Mobile backhaul. Before 4G/LTE moved everything to pure Ethernet, 3G networks, UMTS, relied heavily on ATM. The role ATM was used to connect the cell towers, base stations, to the mobile switching center, MSC. Why ATM? Cell towers needed to carry both voice calls and data simultaneously. ATM's ability to prioritize voice, using CBR service, while letting data fill the remaining gaps, using UBR/abridged, made it perfect for the limited bandwidth copper lines used in early mobile networks. LAN/WAN interworking, LAN, to make ATM useful for businesses, it had to work with existing Ethernet networks. This was done through LAN emulation. Virtual LANs, LAN allowed an ATM network to pretend it was an Ethernet switch. Bridging the gap, a LAN server handled the translation between Ethernet MAC addresses and ATM addresses. This allowed a company to use a high-speed ATM backbone to connect two traditional Ethernet offices in different cities as if they were on the same local network. Broadband ISDN, BISDN. BISDN was the vision and ATM was the technology. The concept, in the 80s, the ITUT envisioned a future where every home and business would have a single fiber optic digital pipe, BISDN, providing high-definition TV, video conferencing, and high-speed internet. The reality, while the full BISDN vision never reached every home, it became the foundation for ADSL. If you have ever seen PPPoE, point-to-point protocol over ATM, in your router settings, that is a direct legacy of the BISDN/ATM era. Summary of usage application. How ATM was used. Status today. Backbone unified voice/data carrier over fiber. Mostly replaced by IP/MPLS. Mobile connecting 3G towers to the core. Replaced by carrier Ethernet. ADSL transporting data from homes to the ISP. Being replaced by fiber, GPON. Business connecting distant offices via LAN. Replaced by SD-WAN and VPNs. Advantages of ATM. Quality of service, QoS. This is ATM's greatest strength. It can guarantee specific bandwidth and low latency for critical traffic like live video. Predictability, because cells are always the same size, there is very little jitter, variation in delay. Scalability, it works efficiently at speeds ranging from a few megabits to many gigabits per second. Integration, it handles voice, video, and data on a single physical network. Limitations of ATM. Cell tax, the 5-byte header on a 48-byte payload creates about a 10% overhead. This makes it less efficient than modern Ethernet for pure data transfer. Complexity: setting up and managing ATM networks is significantly more complex and expensive than IP-based networks. Overtaken by IP/Ethernet, as Ethernet speeds increased, 1 Gbps, 10 Gbps, and beyond, and MPLS, multi-protocol label switching, was developed, the need for ATM's complex cell switching diminished. Summary: ATM was a visionary technology that attempted to unify all forms of communication into a single, high-speed, cell-based system. While it has largely been replaced in the last mile and core networks by IP and Ethernet, its concepts of virtual circuits and quality of service paved the way for modern networking protocols like MPLS. To understand how ATM cells carry multiple services over optical networks like SONET/SDH or DWDM, it is best to view the network as a multi-layered cake. ATM acts as the intelligent middle layer that organizes diverse traffic, while the optical layers act as the high-speed transport. The mapping process, from service to fiber, the journey of a piece of data, like a phone call or a web page, into an optical network follows a strict hierarchy. Step A, the adaptation, AAL layer. Before entering the optical line, different services are converted into 53-byte cells. Voice/TDM, handled by AAL1, which ensures timing and constant flow. Video, handled by AAL2, allowing for variable bit rates. IP data, handled by AAL5, which packages large packets into cell sequences. Step B, the multiplexing, ATM layer, multiple virtual channels, VCS, carrying these different AAL types are bundled into virtual paths, VPS. This allows a single optical link to carry thousands of different conversations simultaneously, each with its own quality of service, QoS, priority. Carrying ATM over SONET/SDH. SONET, North America, and SDH, International, are time division multiplexing, TDM, systems. They provide fixed envelopes of bandwidth called synchronous payload envelopes, SPE, or virtual containers, VC4. Cell mapping: ATM cells are placed into the SONET/SDH payload row by row. Because ATM cells are fixed at 53 bytes and SONET frames are also fixed in size, the cells align neatly, though they can straddle frame boundaries. Scrambling: to prevent the optical hardware from losing synchronization, which happens if there are too many zeros or ones in a row, the cell payloads are scrambled before being placed in the SONET frame. The hex hunt: the receiver uses the header error control, HEC, field to find the start of the cells within the continuous stream of the SONET payload. Carrying ATM over DWDM. DWDM, dense wavelength division multiplexing, is the layer below SONET/SDH. It doesn't care about cells or packets, it only cares about light. Wavelength assignment: in a DWDM system, an ATM switch might output an optical signal, like an OC3 or OC12. The DWDM equipment takes that signal and assigns it a specific color, wavelength, of light. Multiple pipes: a single fiber can carry 80 plus wavelengths. One wavelength might carry an ATM over SONET stream, while the wavelength next to it carries pure Ethernet. Transparency: to the DWDM system, the ATM cells are transparent. The DWDM system just moves the photons from point A to point B. Why use this combination? Telecom providers combine these technologies to get the best of all worlds. Technology: what it provides ATM granular control, can prioritize a voice cell over a data cell. Reliability: provides self-healing rings that can reroute traffic in 50 milliseconds if a SONET/SDH fiber is cut. Massive capacity: multiplies the capacity of a single fiber strand by 80x or DWDM more. Summary of the stack: 1. Service, voice, video, IP, 2. ATM layer, cells with VPI/VCI, priority and routing, 3. SONET/SDH layer, frame/containers, timing and protection, 4. DWDM layer, wavelength/photons, physical transmission.